Welcome back. Now we are moving into the next section, the wave properties of particles. In the last few classes we were discussing particle properties of electromagnetic radiation, and through several effects we saw the explanation of those effects like photoelectric effect, the black body radiation, the Compton scattering. All these required radiation to be, or radiation has to be considered as particles. Now we move on to the next section where we discuss wave properties of particles. The main theme of this section is a moving body behaves in certain ways as though it has a wave nature. So this is what we discuss in this section. The theme is a moving body behaves in certain ways as though it has a wave nature. Now we know in the last chapter, the last section, we had seen a photon of frequency nu has a momentum p that is equal to h nu over c, where h nu is the energy. This relation actually comes from relativistic mechanics. In relativistic mechanics, we know if the rest mass of a particle is 0, the energy and momentum are related by E equal to Pc. So P is equal to E by C. So energy here it is h nu. So momentum P is equal to h nu over C. Now we know C is equal to nu lambda. This is the equation for a wave connecting velocity, frequency, wavelength. So C is equal to nu lambda. So if we give that here either for nu or for C, I will get P equal to h by lambda. Momentum of the photon is equal to Planck's constant over its wavelength. Okay, so the wavelength of a photon is therefore specified by its momentum according to the relation photon wavelength lambda equal to h by p. Now de Broglie suggested that the above equation is completely a general one that applies to material particles as well as to the photons. Okay, so without any experimental support and all, he just suggested that the above equation is completely general one. Lambda equal to h by p is a general equation that applies to material particles as well as to the photons. Okay, so if we apply that equation to the material particles, we know the momentum of a particle of mass m and velocity v, that is given by p equal to mv. And if the particle is moving at relativistic speeds, we have to consider the equation gamma m0 v, because at relativistic speeds gamma, the mass varies and the mass of the particle is related to the rest mass by the relation m equal to m0 over root 1 minus v square by c square. So the gamma here, that is the relativistic factor. Okay, so the de Broglie wavelength here, that is given by lambda equal to h by mv, that is equal to h over, for m I can write gamma m0, where m0 is the rest mass, m is the mass when the particle is moving, so that is equal to h by gamma m0 v, where gamma is the relativistic factor. Okay, now as in the case of electromagnetic waves, this actually de Broglie suggested as a hypothesis. Later this was verified Now, as in the case of electromagnetic waves, the wave and particle aspects of moving bodies can never be observed at the same time. Okay, in the case of electromagnetic radiation, we saw it has got particle nature and wave nature. Okay, and certain effects, to explain certain effects, we need the particle nature. To explain some other effects, we need the wave nature. But we know, even though the radiation has particle and wave nature, the wave and particle aspects of the electromagnetic radiation can never be observed at the same time. So, as in the case of electromagnetic waves, wave and particle aspects of the moving bodies can never be observed at the same time. Okay, so we therefore cannot ask which is the correct description, whether it is particle, whether it is wave. Okay, you know, in the electromagnetic radiation, there was a section called what is light, what is electromagnetic nature. So what is electromagnetic radiation? And we saw we can only say it has got particle and wave nature, that is dual nature. So here also we can say the particle has dual nature. Okay, wave nature and particle nature. So all that we can say is that in certain situations a moving body resembles a wave, and in others it resembles a particle. In certain situations it behaves like a wave, and in certain other situations it resembles like a particle. Okay, now which set of properties, which properties is most notable in a situation depends on how its de Broglie wavelength compares with its dimensions and dimensions of whatever it interacts with. So which property, the wave nature or the particle nature, that becomes notable. Okay, which property dominates, that is determined by the dimensions of the particle and the dimensions of the whatever it is interacting with. For example, for a bullet fired from a gun, if you calculate its de Broglie wavelength, its de Broglie wavelength will be very small compared with the dimensions of the bullet. If you calculate the de Broglie wavelength of a car moving with a certain velocity, the de Broglie wavelength will be too small compared with the dimensions of the car. So you can consider at that situation the car is behaving like a particle or the bullet is behaving like a particle. Okay, but if you take an electron in an atom, the electron, if you calculate the de Broglie wavelength of the electron, we can see that the wavelength of the electron compares with the dimensions of the atom. So we have to consider electron in an atom as a wave. Okay, so which set of properties is most notable depends on how its de Broglie wavelength compares with its dimensions and the dimensions of whatever it is interacting with. Now, an interesting question, waves of what? Waves of what? We have been seeing a particle as a wave associated with it. So waves of what? Why this question? We know in water waves, the quantity that varies periodically is the height of water surface. In sound waves, it is a pressure that varies. In light waves, the electric and magnetic fields vary. So when we talk about a wave, there will be some quantity that is varying in space and time. So in matter waves, in de Broglie waves, what is varying? That is the question. Waves of what? So what is it that varies in the case of matter waves? Okay, the answer is the quantity whose variations make up matter waves is the wave function. So the quantity that varies in matter wave is the wave function. Okay, the value of the wave function associated with a moving body at a particular point in space, which is represented by x, y, z, and at a time t, that is related to the likelihood of finding the body there at that point x, y, z, and at the time t. Okay, So the wave function is the quantity that varies or whose variations make up matter waves. Okay, now the value of the wave function of associated with the moving body at a particular point in space x, y, z at the time t is related to the likelihood of finding the body there at that time t. Okay, now the important point is the wave function psi has no direct physical significance. Okay, the wave function psi has no direct physical significance, even though it is the variations of psi that produces matter wave. The wave function psi has no direct physical significance. Why? The probability that something be in a certain place at a given time must lie between 0 and 1. Okay, the probability that we know, we have said the psi is related to the probability of finding the body there at the time. Okay, the probability of finding the body there at the point x, y, z at the time t. Okay, so the probability that something be in a certain place at a given time that must lie between 0 and 1. 0 means the object is not definitely there. Probability is always between 0 and 1. 0 means there is 0 probability. 1 means the probability, the maximum value is 1. Okay, so if the probability that something be in a certain place at a given time must lie between 0, 0 means the object definitely not there, and 1, that means the object is definitely there. An intermediate probability, say 0.3. Okay, probability I told can vary between 0 and 1. An intermediate probability, say 0.3, means there is 30% chance of finding the object at that point, at that time. Okay, but amplitude of a wave, the instantaneous amplitude of a wave, can be negative as well as positive. The wave, the variations, the wave function, that can be positive as well as negative. And a negative probability, say minus 0.2. When psi takes the value minus 0.2, we cannot say what is the probability, because negative probability is meaningless. Okay, so psi cannot be directly related with the probability, because a negative probability, the psi can be both positive and negative, but a negative probability is a meaningless one. Okay, hence psi itself cannot be an observable quantity. Hence psi itself cannot be an observable quantity. Okay, so the wave function psi has no direct physical significance, because psi is related with the probability. Psi has to be related with the probability that we saw first. But if it is directly related with the probability, then it can take positive and negative value, but negative value is meaningless because probability cannot take a negative value. So psi itself cannot be an observable quantity. But this problem is not there for modulus psi square, the square of the absolute value of the wave function psi. Okay, because if you take the square, modulus square, it will be definitely positive. So this problem is not there for modulus of psi square, the square of the absolute value of the wave function psi, which is known as the probability density. Okay, modulus of psi square, this is known as the probability density. Okay, so the probability of experimentally finding the body described by the wave function psi at the point x, y, z at the time t is proportional to this probability density modulus of psi square there at time t. Okay, so the probability of experimentally finding the body described by the wave function psi at the point x, y, z at the time t is proportional to what modulus of psi square there at the time t. So psi is thus related with the probability through this probability density. So psi doesn't have any direct physical significance. It is a mathematical quantity, but if you take the square of its the square of the absolute value of the psi modulus I square, that will give you the probability. Actually, that is probability density, so it will be proportional to the probability. A large value of modulus I square means a strong possibility of body's presence, while a small value of modulus I square means a slight possibility of its presence. Okay, because modulus I square is proportional to the probability. Okay, actually modulus I square is probability density. So if you multiply modulus I square with the volume, you will get the probability. Okay. Now this interpretation of the wave function was first made by Max Born in 1926. So we are using this interpretation throughout this section. Okay. Now another important point is, although we can speak of the wave function psi that describes a particle as being spread out in space. So psi is spread out in space, the wave function that is actually varying in space. This does not mean that the particle itself is thus spread out. So psi, the wave function that varies in a matter wave, that is spread out in space, but that does not mean that the particle itself is thus spread out. So if a wave is associated with electron, that does not mean that the electron is spread out in the space. Okay, only the wave associated with the electron, that is spread out in the space. Okay, so when an experiment is performed to detect electrons, for example, a whole electron is either found at a certain time and place, or it is not. Okay, there is no such thing as 30% of an electron. Okay, suppose that modulus of psi square, the probability density, that is its value is 0.3. Okay, or the probability is 0.3. That does not mean that if you try to experimentally try to detect an electron, you will get 0.3 part of the electron. You will either get a whole electron or no electron. Okay, then what is meant by that 30%? The 30% means that there is a 30% chance that the electron to be found at that time and place, and it is this likelihood that is specified by the probability density. Okay, so the particle itself is not spread out in space, in time. The probability for finding the particle, that is actually spread out. The wave function is spread out, the probability is spread out. Okay, so that it is possible for 30% chance that the electron to be found at that time and place, and it is this likelihood, that is this probability, that is specified by modulus of psi square. Now, while the de Broglie wavelength associated with the moving body can be found using the equation lambda equal to h by mv, finding their amplitude psi as a function of position and time is often a very difficult thing. Okay, some special methods will have to be used for finding the wave function psi. So de Broglie wavelength of a particle moving with a certain velocity or certain momentum can be easily found using lambda equal to h by mv, while finding the amplitude psi as a function of position and time is difficult. So how to calculate this psi, that will be discussed later in the later sections. Okay, until then we assume that we know as much about psi as the situation requires. So we assume that we completely know psi. Okay, for the discussions that are going to follow, we assume that we have complete knowledge of the psi. Okay, how to calculate psi, that will be discussed later.